Most of us picture the universe as something that is static. Stars shining, galaxies drifting, everything quietly expanding into the void. But that picture is incomplete. On the larger scales, the universe is not tidy or still. It forms a cosmic web. Filaments of galaxies and gas stretch across hundreds of millions of light years, connecting galaxy clusters like a three-dimensional spider web. And inside that web, something extraordinary has just been spotted. A team of astronomers working with data from South Africa's Meerkat Radio Telescope has identified one of the largest rotating structures ever observed in the universe. A filament roughly 50 million light years long, not only full of galaxies, but spinning. To put that into human scale, imagine a carousel, except each os is a galaxy. Each galaxy contains billions of stars, and the whole carousel stretches across a region of space far larger than our entire local group. This matters because rotation or angular momentum is one of the key organizing principles of the universe. Planets rotate, stars rotate, galaxies rotate, but rotation on scales this large, 50 million light years, is something cosmologists didn't expect to find so clearly. And there is another twist. This discovery depends on quantum physics. The entire signal comes from a quantum spin flip transition in neutral hydrogen, the famous 21 centimeter line. A tiny quantum event inside an atom becomes a tool for marking the skeleton of the cosmos. And it gets better. This story is African. The observations were made with Meerkat in the Karoo, which is one of the quietest radio environments on Earth, and part of a long-term effort that is turning Southern Africa into a global hub for precision radio astronomy. Today, we are going to unpack all of that. The science, the quantum foundation, the implications for cosmology, and Africa's growing role in frontier astrophysics. I'm joined by one of the researchers behind the discovery, Dr. Madalina Tudorache. Dr. Madalina is a University of Cambridge affiliated postdoctoral research assistant at the University of Oxford working on large-scale structures. Her main research interests lie in galaxy evolution and observational cosmology. Dr. Madalina, thank you for joining us today. Congratulations on the paper. The way I would like us to start is in your own words, you can explain what exactly you detected. Is it a rotating filament? Is it a coordinated systems of galaxies? And how do you think we should think about this discovery?
So basically, I think the main thing is when you think about galaxies and the way galaxies exist in the universe, our current working theory is basically that they organize in these large structures, in filaments, voids, clusters. So for example, clusters is where a lot of galaxies are very much clumped together. Voids are emptier regions of space. As filaments, you just have the galaxy oriented along these thin highways, you could call them, between these clusters, where you also have things like gas, dust, and all these all kinds of matter. Basically, what we found is we originally found 14 galaxies which were detected in neutral hydrogen, and they were just in this straight line. And they were very surprising because we didn't really expect them to just look like a straight line. So we basically after that investigated, wanted to see if they're actually part of something larger. And when we looked at all the actual optical galaxies in that specific region of space at that specific interval, we basically saw that there was only one thing. It was this very big filament, and these 14 galaxies were part of it. But we had another basically roughly 200-ish more galaxies in the structure. So we're okay, this is very interesting. The fact that we can actually see this clearly, we can see this neutral gas in these galaxies that are part of this filament, was actually quite interesting. So okay, should we actually look at the dynamics? Is there anything interesting happening within this filament? And that's how we basically discovered when we were looking at it, is that the galaxies were moving based on the spine of the filament away from us or towards us, which basically gave us the idea that, this is probably rotation. So they are actually rotating around the spine of the filament.
Yeah, thank you. So was rotation on this scale expected, or was this a genuine surprise to you?
It was a surprise in the sense that, so it has been predicted theoretically. We have, there's only been a very, very few papers that have dealt with it. So I remember when we first found it, there was only one theoretical study and one observational paper that did just on millions of filaments, to kind of put them all together and try to see if they see any signal of rotation. So there were two papers. In the process of writing this paper, there have been another paper, which also did the exact same method of just putting all of them together, appeared. But we were the fact that we actually managed to see it in one singular filament was what was really surprising. So the theory behind it, it's not a complete shock. We would expect some of these objects to exist, but because of the capacities we've had with telescopes and how to measure these things, we haven't been able to. It was a surprise that we actually just found them. We found one object that actually did it.
Okay. Another question is, how do we know we are seeing rotation and not shear or infall?
So it's a bit harder to be 100% sure, because basically we don't really see exactly what happens up and down, right? We haven't really looked if there's any kind of flow, which is something that we would be interested in doing. We actually we applied for more time on the radio telescope to be able to see all the way down to where we think the end of the filament is, to see if we still see neutral hydrogen, if it's is this whole thing falling into a cluster? We don't know. We are going to currently investigate, but with the current data we have and with the current statistical checking that we did, it's more likely to be rotation than anything else.
Okay, and you mentioned the telescope, and what made that particular the Meerkat the right instrument for this purpose?
I mean, Meerkat is probably one of the best radio telescopes we have so far. Until SKA comes online, Meerkat has been the gift that keeps on giving. Across a lot of radio astronomy fields, if you look at transients, if you look at neutral hydrogen, if you look at any of these things, Meerkat has been delivering very, very good results because it has very high sensitivity. So we're now dealing with stuff that we haven't really had the capacity to observe before. So basically it's been very important to have access to such a telescope to be able to actually detect, especially for the neutral hydrogen part, because we would not be able to get the dynamics of the gas as well with any other telescope.
How important was the 21 centimeter hydrogen line for detecting rotation?
So basically we use the emission line in neutral hydrogen to calculate how the gas moves, and from the way you calculate the gas moves, that's how you can calculate how the galaxy rotates itself. So the neutral hydrogen, we mostly use it to see because the other interesting part of this filament is not only that the galaxies are rotating around the filament, the rotation was aligned with the spine of the filament. So let's say if you have a galaxy rotating and you kind of try to draw a vector up, or in whatever direction the rotation is, what we also found is that, especially for the neutral hydrogen galaxies, they were aligned. So the rotation was coordinated basically within the filament, and that we'd have not been able to observe as well if we didn't have access to neutral hydrogen. So the signal was strongest in the galaxies where we had neutral hydrogen, and we measured this rotation within the galaxy with the neutral hydrogen.
So how close were you to sensitivity limits, and where did the heaviest data processing happen?
In some of the galaxies were quite we barely had one or two spectral bands. Some of the galaxies, some of the neutral hydrogen ones were quite close to the limit we could push, but a lot of them were actually fairly well resolved and everything. I mean, all the data and all the processing was done on, if I remember right, I think it was done on IDEA. So it was the computer down in South Africa. It basically hosts most of the data that we get from Meerkat, and specifically for MITI, which is the survey that I'm part of that has dealt with the data, with the neutral hydrogen emission line data that we've used across this work.
Yeah, okay. So what does this mean for our understanding of how galaxies acquire spin?
So this is quite important, I think, for our understanding of how galaxies react to their environment, and specifically the way we understand how gas is affected by the large scale structures. So do we know if it gets stripped out of the galaxy, if it still keeps in the galaxies, its dynamics affected? So there's a lot. So there's basically things about understanding how galaxies form and how the filaments themselves form. Because the thing is, what was really interesting about this filament, it was basically how young it is. It hasn't fully collapsed, because if we have fully completely formed, we have not expected to still see a lot of neutral hydrogen in it, because all this neutral hydrogen would have been expelled away. So seeing all these structures, it's really important for us to basically understand a lot more about on their formation on the side of the large scale structures, but also understanding on the galaxy side how the galaxies interact with the large scale structure. And that's a very important thing for us to understand galaxy evolution.
Do existing models, do they accommodate rotation on this scale, or does this discovery push theory?
I don't think it fully pushes theory. I think we can basically kind of predict, depending on, so not all cosmic web filaments would be able to support rotation, but depending on where they are, like intersection of walls or like intersection of clusters that could imprint this angular momentum, it's not unfeasible. Like, it is not in every single filament, but it is something that we can model and predict theoretically.
So how have theorists, how have they reacted so far?
We've had a few emails we've had from across like astronomy and theory about like different theories, like that theories that could like explain things. So it hasn't been like this explosion of like, oh my god, this is completely broken everything. It's like, oh, this is cool. Yes, we can explain this with this. So it's been a welcome reaction. It's been.
So talking of location of the telescope, how much of this finding is hinging on the radio quiet sky of the telescope's location?
I mean, that's really important. And actually, this was an anecdote we had some time ago, is when we were reducing data that was taken in 2020, it was actually higher quality as well, because there were fewer planes going across South Africa because of the pandemic. But its location is really important to us because we need these radio telescopes because it's an interferometric radio telescope. The fact that it's in the Karoo Desert, it makes our lives so much easier when it comes to like reducing data and getting like the most we can out of our data.
So what insight taking a step back now and looking at these results, what insight does it give us about the region and African continent's potential roles in radio astronomy?
I mean, what I think is basically tells us that the fact that Meerkat is there, it's such a plus, and that we should really be involving, because a lot of the work done then has been done in South Africa by people in South African universities, like people in Cape Town, UCT, and all of that, and it's been incredible to work with these people. And I think it's great that we have this community where we can actually not only do science, but actually like help people there and like help people like bring our science community together, because basically this is proof that when we do something like this, we can achieve discoveries such as the one we did, right?
Yeah, and does it give any indication regarding what SKA might potentially reveal?
Yes, so SKA should be able to find more of these things, just full stop. Like when SKA is going to come online, we should be able to find more of these like individual rotating filaments, because we're going to have access to a much larger patch of sky, and we're going to have access to basically be able to find a lot more neutral hydrogen galaxies. So basically that means, and then in synergy with optical telescopes such as either Vera Rubin or Euclid, who are also looking in optical data to be able to actually trace these large scale structures, we should be able to get so many of these, so we can actually build a statistical sample and be able to describe these objects instead of just having one object, to actually see if there's any trends in like how they all behave, like is there specifically anywhere they prefer to exist, or there's any conditions they're more likely to have these rotating filaments. But yes, I think the advent of SKA is really, really exciting for us.
Then another angle I want to explore with you is the quantum angle. And these whole measurement is resting on a quantum spin flip transition. And do you think that connection between quantum physics and cosmic structure gets enough attention?
I mean, they're such at wild different scales that it's probably quite hard to say. I think we're so used to working in such different regimes that I think, especially in this scenario, I guess, because the spin flip transition basically helps us detect the hydrogen, but that's a completely separate process from anything that happens to the gas after like this line is emitted, right? So my answer for now would be no. Though that isn't really a link. It's just we just happen to work with something that we can detect from one regime, but everything else happens at such a different regime that they're completely separated.
Okay, I'll take that. So when did you first suspect you were seeing actual rotation personally?
I think because we spent a lot of our time at the beginning just looking at the alignment and just basically seeing that the spin of the rotation inside the galaxies was basically oriented quite close to the filament. And we're like, well, if we have actually this is like a few months after we're doing this, it's like, oh, let's just look at like how, like, because we're also trying to measure the radius of this filament. So trying to basically see from distance from the spine to where, so basically see where all the points go away. So we're doing this like plot of like the velocity of the galaxies versus the distance. And when we looked at it, it's like, wait, that does look suspiciously like a curve. So like, okay, this might be rotation. So then we basically switched our gears, like, okay, this could be rotation. So this is a few months into actually looking at the structure.
What was the tipping point for the team that, yes, this is what we are looking at?
I think it was basically after that plot, we started like fiddling around it, like fitting different models, and we saw that like, okay, that actually fits. And we literally did like, I think 3 of us did it differently just because we're like, if this is real, we need to be sure this is real. Because we're like, oh yes, this could be rotation, this is great. But having had like 3 different people do the same experiment to see if we get the same results, and when we did, we're like, yeah, no, this is actually rotation.
Yeah, what's next? What do you hope to explore next?
So, as I said, I think we're basically looking at getting more time on. We've got more time on the radio telescope, MeerKAT, so we can actually look along down this filament itself to see if we do see things like flows and like basically make sure that this is nothing on that side. So that's quite interesting. I am now more involved into where we've been. So I'm more interested in actually looking just at large-scale structures in general. And if we happen to find something there as well, that would be actually quite cool.
What should be the most important aspect of this research that almost every person should care about?
It's a good question. I mean, it was really funny when I had all the other interviews. Some people were asking about aliens and things. It's like, I don't think I can quite connect it to that. So I think, unfortunately, there's nothing there. But I think, well, I think the technology itself is important for everyone, right? Like getting better and better radio telescopes just develop, like for example, Wi-Fi was basically developed because of like radios. So I think on the technical side, the fact that we're able to get this technology that helps us get such a discovery is important to everyone, right? A better understanding of radio technology is incredibly. And I think, I don't know, maybe at the personal level, I just think it's really cool to see that we're getting a better and better picture of understanding the cosmos and how things formed. Because I guess in a way that gets us closer to understanding how our galaxy formed, how our solar system formed, how our planet formed, right? It's just because we don't have such a big grasp on how all the other galaxies formed, let alone ours. And I think getting just small incremental steps towards understanding a theory where we describe like the formation of matter and the formation of all these things should be interesting to us, because in the end, we also formed here.
Do you think the result now reshapes how we picture the universe, not just as something expanding, but something that is moving, rotating, and evolving in ways we are only beginning to see? What do you think about that perspective?
I think that the universe is a beautiful chaos, if you want to say something. It's very much, it still expands, it's so dynamic. The fact that everything, things in it just don't just like radially just like expand. The fact that there's so much interaction, there's so many things going on around it, I think is just fun, I would say.
It seems to be a true result of collaboration. For instance, look at you personally. You work with the University of Oxford, you're connected to the University of Cambridge, worked on a satellite in South Africa. And I think this industry, this line of research relies a lot on collaboration and connection. Not just of people, but also of tools.
Yes.
Looking at the current dynamics, I'm not trying to drag you into politics, but I'm looking at the bigger scheme of how things are going at the moment. How protected or how insulated is astrophysics and cosmology and this network and partnerships that are at the bedrock of good astrophysics findings? How protected are they from what is happening outside of science?
I think, fortunately or unfortunately, depending on your point of view, we are quite a bubble, right? Like, academia has been historically in quite a bubble. And yes, you can definitely see problems in the US, for example, which is probably the best example of like how some of these bits of the bubble actually start bursting because the university is no longer protected and there's interest financially, blah, blah, blah. But I think, at least across Europe and across, even to some extent in the US, like I think we're still in such a bubble that most people have been able to just go around with their lives and do their own do their research. And I think it's important to acknowledge that it's not always fine. And because people come from different backgrounds, people are affected differently by the politics of where they live, financially as well, right? The problem with a lot of like our collaborators in the African continent is it's quite hard for them to come to Europe because the financial strain is so much harder on them than it is for us to go down to South Africa, for example, right? So there's all these things that we can't fully say, oh, we're so isolated in our completely bubble and nothing affects it from our side, because that's not true. That would be a disservice to the people that actually are affected to be completely like ignore this thing. But I think learning to work in this framework where it's a kind of a bubble, but still having to be very aware of people's backgrounds and the financial part of the institutions and all of that. I think it's actually quite good for us to just like teaches us how to like collaborate better, right? And when we collaborate better with people, we get better results, as it's been basically proven, right?
There used to be this perception regarding it used to be scientists in developed parts of the world, okay, let's say in the UK and the US, come to Africa, get the data and go. In this conversation, you've actually highlighted how much of work was done locally. So I want you to give me more, I want you to expatiate more on that. So let's highlight what was actually locally done in this research in Africa.
So personally, I didn't, some of the data was reduced by my collaborators, so I haven't actually done any of the data reducing myself. Basically, I got the neutral hydrogen data, so on that side, I wouldn't be able to tell too much, but basically, we store, because there's so much data coming out of Meerkat, all of the data is stored in South Africa. Like it would be just physically impossible for us to transfer everything there. And why would we? People in Surveyor do such a great work dealing with all these problems about the data, about the transfer, about making it so smooth in terms of actually, this is the raw data, this is the pipeline. You guys just kind of like, we can just, it's all stored locally, it's all organized locally. You guys can just do what you need, and then you can then get the data reduced, and then you can get the data to you. So it's basically the work is done there, and it's great to be done there, right? So
Absolutely.
we don't have to. It makes our life easier as well, because we don't have to like, they've built all these structures already that they make things for us easier for us. But not just to go there and take stuff, is to like actually talk to them and understand the way they've done things, which maybe have been slightly different from the way we would have done things. But like, this also has helped on both sides to make like things smoother, right?
Yeah.
So I think that's something really important.
Yeah, that was really, really lovely. So we're at the beginning of a new year. What are you looking forward to in 2026? And are there any key, potentially important, forward-looking insights that could be very, very important to this line of research coming in this year?
I mean, hopefully so. As I've said, Vera Rubin has come. We've got data from Vera Rubin coming up soon, and basically, I think we've got more data on Meerkat. We've got all of these things, so we're definitely still following. We're still following along this trail to see if we find anything interesting. So hopefully, knock on wood, we will have more interesting results this year as well.
So what was your journey like? How did you venture into astrophysics? There are so many career opportunities, so many lines of things you could have done. I'm not talking about you as a doctorate or as a science person already, but when you were probably young, let's say, at what point did you start getting fascinated with this line of work, not just professionally, but as a young person?
So I'm originally from Romania. I'm not from the UK. And basically what this means is I lived in a small town where you had quite clear skies. And I remember my father used to take me outside to look at the sky. And I actually wanted to be an astronaut, but turns out I have very severe motion sickness. So I could never actually be an astronaut. So I guess I just then settled to what I thought was like the closest thing, which is actually like understanding the stars and things like that. And then I kind of worked out, and I was in middle school that I'm actually quite good at physics. So
So what excites you personally that doesn't make you get bored just staring and looking and exploring those things? What excites you?
I think it's basically, and I think as I've said before, it's fun. Like I think people often talk about how insignificant we are in the like massive universe, but like the universe itself is not just like massive static thing. Like things move in the same way we move around, and it's just very exciting to live in a place. It's the entire universe. Things are just kind of like always happening, and it's just really exciting to kind of pick at these things and see like this is something that happens maybe like trillions of millions of like light years away from us, but it's kind of like, I don't know, it's just exciting.
So what is your last remark for me? What is your last message for me before we close it out?
I'm not sure. I don't know. I think it's a really exciting time, especially for the field I'm in, and especially with like all the stuff that comes up online, like all the telescopes, like as I mentioned, Vera Rubin, Euclid, SKA, all these things. The fact that we're able to do these things and we're able to maintain, like, be able to do science even in a, as you said, a quite turbulent world. I think it's something really important, and I think it's something that we really need to like keep striving for.
Yeah, that was beautiful. Thank you so much. Thank you very much. I enjoyed this. Okay.
Thank you so much. Thank you.
Congratulations and good luck.
Thank you. Thank you. Bye-bye.
Bye.